So good morning everyone and welcome to this brand new class. In this class we are going to start with magnetic effects of current. Now what do you mean by magnetic effects of current? Any idea anyone? What is magnetic effects of current? What do you mean by magnetic effect of current? Everyone has seen a magnet, yes or no? Everyone understands what is a magnet.
Yes, sir.
A magnet creates something known as a magnetic field. Now, if you look at the magnet, the simplest magnet that I can draw would be like this. Yes or no? It has a north pole and it has a south pole. Uh, that's a magnet. Now, we call it bar magnet because it looks like a bar. That is a magnet. Now, whenever we talk about any magnet, every magnet has two poles. Yes or no?
Yes, sir.
Every magnet has two poles. Can you create a magnet which has only one pole? Can
No,
you have
sir.
a magnet which only has a north pole or a south pole? No. Every magnet would always have two poles. So we write it like this: magnetic monopoles. Magnetic mono means one. Do you understand the meaning of mono?
Yes, sir.
Magnetic monopoles don't exist. So magnet will always or poles will always exist in pairs, right? Now, since there is a pole, every pole has a pole strength. The north pole is given positive pole strength. We just assume that the north pole is positive, and the south pole is taken as negative. So the north pole, if I call it as plus m, the south pole becomes minus m. This m is known as the pole strength of the magnet. What is this m known as?
Pole strength of the
Pole
magnet.
strength of the magnet. Now, if the pole strength is high, the magnet is powerful. If the pole strength is small, the magnet is weak, weak magnet. Now, instead of calling this magnet as a magnet, I can also call it as magnetic dipole because it will always exist in two poles. We understand this?
Yes,
So
sir.
instead of calling a magnet as a magnet, I can also call it as a magnetic dipole. You understand this? Yes or no?
Yes, sir.
Okay. Then two opposite poles will attract each other, and two same poles, like poles repel and unlike poles attract. We know this. Yes or no?
Yes, sir.
Now every magnet has a length. This is known as Lg. This Lg is the total length of the magnet. We call it the geometric length of the magnet. Lg is the total length of the magnet. We call it the geometric length. We understand this? This is known as the geometric length. Geometric length of the magnet. But you must understand that the poles of the magnet are not exactly at their ends. The poles of the magnet are somewhere a bit inside the magnet. The distance between the two poles is known as Lm, and we call this Lm as the magnetic length. This Lm is known as the magnetic length of the magnet. We understand this? The small things that I am just drawing in the same thing. Magnetic length. This magnetic length is always less than the geometrical length, and you can write this formula. magnetic length divided by the geometric length of a magnet is 0.84, something like this. So far, so good? Yes or no?
Yes, sir.
Now, whenever we talk about a magnet, a bar magnet, it's a dipole. It's a dipole. You must understand that this is a dipole. Now, whenever we talk about this magnetic dipole or a bar magnet, we never talk about its pole strength. We never talk about its length or magnetic length or geometrical length. Whenever we talk about a magnet, and I will draw the magnet again because that magnet has become too cloudy. Whenever we talk about a magnet, this is the north pole, this is the south pole, this is plus M, and this is minus M. Whenever we talk about the magnet, we talk about magnet. Every magnet has a dipole moment. We call it magnetic dipole moment. Now, this magnetic dipole moment of a magnet is a vector quantity which is directed from the south pole towards the north pole. This magnetic dipole moment is written by the letter capital M. So capital M is known as the magnetic dipole moment. Magnetic dipole moment. It is a vector quantity, as you can see, and the direction of this vector is from where to where?
Negative to positive.
Mm, South to north.
South to north.
We are calling south as negative. Okay, negative to positive. And the value of this magnetic dipole moment is given by M, the magnetic pole strength, multiplied by the magnetic length. And this magnetic length actually is taken as a vector quantity. Magnetic length is taken as a vector quantity which is from the south pole towards the north pole. So remember, bacho, whenever we will talk about any magnet, we will always talk about this magnetic dipole moment. Every magnet is characterized by a magnetic dipole moment. We understand this?
Yes, sir.
Talk about any magnet, we'll not talk about the pole strength, we'll not talk about the length, we'll always talk about the magnetic dipole moment, which is a vector quantity. It goes from north, no, it goes from south towards the north pole. So far, so good?
Yes, sir.
Now, as soon as we hear that magnetic dipole, that might remind us of a term which we had read in the previous chapter. Does it remind you of any term that we had done in the previous chapter? No? It should remind us of a term which is known as electric dipole. Electric dipole. And what is an electric dipole? It is a combination of two charges, plus Q and minus Q, separated by a very small distance, D. Electric dipole. Now, whenever we talk about electric dipole, it has two poles, one positive, one negative. Magnetic dipole has two poles, north, south, positive, negative. Every electric dipole is also characterized by a vector which is directed from negative charge towards the positive charge. We will write it as P vector. This P vector is known as, this M vector is known as magnetic dipole moment. What is this P vector known as? What is this P vector known as? Electric dipole moment. That is correct, Abhiram. This is known as the electric dipole moment. Electric dipole moment. Electric dipole moment. This magnetic dipole moment is given by m into the magnetic length. Can anyone tell me what will be the formula for electric dipole moment? This is also a vector quantity from negative charge toward a positive charge. What is the value of this electric dipole moment vectorly?
Q into D vector.
Q into D vector, and this D vector is directed from the negative charge towards the positive charge. So both of the terms, both of the things are exactly similar in exactly all aspects. The only difference being is one is a magnetic one, the other one is an electric one. One we have electric dipole moment, one we have magnetic dipole moment. Apart from that, everything is exactly similar. Do we understand this?
Yes, sir.
I'll give you 2 minutes. Have you noted this down, everyone? Or you want time to note it down? I'll give you 2 minutes to note it down. Now, let us move ahead. Now, what does a magnet do? A magnet creates a magnetic field. That is the next heading, magnetic field. Magnetic field. What is a magnetic field? It's a region in space. It's a region in space where a magnetic pole, north pole, south pole, magnetic pole experiences magnetic force. Magnetic field is a region in space where a magnetic pole experiences a force. This is somewhat similar to something that we have already read in the previous class, previous chapter. What is it similar to?
Electric field.
Electric field. What is electric field? It's a region in,
Space where electric pole experiences electric
don't
force.
call them electric pole, where a
Electric
charge
charge. Electric charge.
experiences electric force. Now, every magnetic field will be denoted by a vector which can be called as magnetic field strength, magnetic field intensity, or magnetic field strength, denoted by B vector. Magnetic field is denoted by B vector. Magnetic field strength or magnetic field intensity denoted by B vector. Now, how do I find the value of magnetic field, the strength of magnetic field, the intensity of magnetic field? So, what do? I place a magnetic monopole plus M. Plus M means it is a north pole. Yeah. An isolated north pole is not possible, but this is just to tell you and make you understand how it is. Now, if I place this magnetic monopole which does not exist. In a magnetic field, it will experience a force. Let us say that it experiences a force Fm, M standing for magnetic, Fm. The value of magnetic field at that point will be given by the force experience Fm divided by the, not mass, but by the pole strength of that pole. Magnetic force per unit pole strength. Do we understand this?
Yes, sir.
Electric field or electric field strength or electric field intensity is denoted by the vector E vector. How do I find the value of E vector at any point in space? We have already done that. Can anyone tell me? How do I find the value of electric field at any point in space? I place a charge, positive charge plus Q, in an electric field. If there is an electric field, it will experience an electric force Fe. To find out the value of this electric field intensity, I will divide this electric field by what?
By charge.
By the charge itself. So if I want to find out the magnetic force on any monopole, I multiply M by B vector. Remember, M is not mass, M is the pole strength. If I want to find out the electric field, the force on a charge, I will multiply Q by electric field. Are we able to understand this?
Yes,
Or it is
sir.
going above our head saying bye bye? Bye bye.
Understood, sir.
Okay. If I talk about a North Pole, North Pole experiences force in same direction, as magnetic field. A North Pole will experience force in the same direction. What can we write here? Can we write anything here?
Charge experiences force.
Take a deep breath. See what I have written and then try to do the same thing there. A positive charge will experience force in the same direction as the electric field. I've only written the force on the positive charge. I hope you can understand what will be the force on the negative charge. So, if I have a North Pole and the magnetic field B is this way, sorry, I should draw it in another way. If I have a North Pole and the magnetic field is in this direction, the magnetic field vector is in this direction, it will experience force in the same direction. If I have a South Pole and I have the magnetic field in this direction, The south pole will experience force in the opposite direction. Taking the analogy here,
Sir.
if I have a positive charge plus Q, and if I have an electric field in the same direction, electric field in this direction, this will experience force in the same direction. Electric force we will call it. If I have a negative charge minus Q and I have an electric field in this direction, this charge will experience force in the opposite direction. Magnetic field is a vector quantity. We have seen that it's a vector quantity. Its SI unit is Weber. Weber is written as WB per meter square. Or you can also call it Tesla. You might have heard this word Tesla. Electric field is also a vector quantity. The SI unit is volt per meter. Or you can also call it Newton per coulomb. I hope you are able to understand what is happening here.
Yes, sir.
To understand electric field, we draw electric field lines. Electric field lines start from where? Start from positive charge and end on negative charge. If I have a plus Q charge, electric field lines will go like this. It will go away. Do we remember this? Yes or no?
Yes, sir.
Electric field lines start from a positive charge. If it is a negative charge, electric field lines will come towards the charge. We remember this. Electric field lines have a starting point. Electric field lines have an end point. They start from a positive charge and they end on a negative charge. Positive and negative charge can exist on their own. But the problem with a magnet is magnet cannot have one pole. So magnetic field lines do not have starting or end points. Does not have starting point or end point. Magnetic field lines are in closed loops. They're always in closed loops. What do you mean by closed loop? if I draw the magnetic field lines of a bar magnet, remember magnetic monopoles do not exist. So I cannot have one pole existing in this universe. It does not exist in this. This is how the magnetic field lines are there for a bar magnet. I hope you have seen this. Outside the magnet, they are going from north to south. I hope you can see this. Outside the magnet, they are going from north to south. That is outside the magnet. They are going from north to south. But you can see inside the magnet, they are going from south to north. So they do not have a starting point. They do not have an end point. They are in closed loops. If something is moving in a loop, you don't know where it is starting and where it is ending. So outside the magnet, the magnetic field lines are going from north to south. Inside the magnet, they are going from south to north, and therefore they do not have a starting or a end point. Are we able to understand this? Yes or no? No or yes?
Yes, sir.
Have you noted it down till here? Shall I move ahead? Huh?
1 minute, sir.
Okay. Let me know once you are done. We move ahead. Now, what is the next thing that we see? We are continuing. On one side, we are continuing with electric field, and on the other side, we are continuing with we are doing magnetic field. Now, if you have a point charge, so I can write here electric field due to a point charge. Electric field due to point charge. Electric field due to a point charge. If I have a point charge plus Q, this point charge creates a field at point P. Yes or no?
Yes, sir.
The direction of that electric field, everyone knows. The direction of that electric field is like this, going away. If the distance is r, we also know the magnitude of that electric field. What is the magnitude of that electric field due to a point charge at a distance r? No one remembers it? Okay. It is 1 by 4 pi epsilon naught q by r square. That was the value of electric field created by a point charge. Please note it down if you have forgotten. Now, similar to electric field due to a point charge, we can write the formula for magnetic field. Now, magnetic field, instead of E, write B. Magnetic field due to monopole. Remember, monopole do not exist. But still, theoretically, we can write the magnetic field due to a monopole. If I have a plus M pole, which is nothing but a north pole at this point P will create a magnetic field which will go like this, B vector. If I call the distance of this point from the magnetic monopole, North pole as R, the value of magnetic field B would be mu naught by 4 pi m by r square, where m is the pole strength of that monopole. I hope you can see the similarity in the formula. The similarity in the formula. Here we have M. Here we have Q. M or Q has been replaced by M. Here we have 4 pi. Here we have 4 pi. So that is similar. R and R are similar. The only other difference is epsilon naught is in the denominator here, but mu naught is in the numerator here. So wherever epsilon naught comes in the denominator, mu naught comes in the numerator. Why is that so? You should remember that mu naught into epsilon naught is 1 by c square, where c is the speed of light. So these two are related to each other with this formula. Mu naught into epsilon naught is 1 by c square, and therefore you will find wherever mu naught comes in the numerator, epsilon naught comes in the denominator. I'll give you 2 minutes to note this down. Once you have done, please let me know. Then let's move ahead and come to the point where what is more concerned to us at this point in time. That is what that concerns us more. Everything else is just okay. Electric field due to a dipole. This is what we have to understand, because whenever we are in magnetism or magnetic field, monopoles do not exist. Now, if you remember, we had done this field for 2 points. The first one is known as the axial point. The axial point. Now, what is this axial point? If I have this as the minus q charge and I have this as the plus q charge, the axial point is a point here, P, whose distance from the center of the dipole is given as r. And if you might recollect, the electric field was in this direction, the same direction as the dipole moment. The dipole moment of this dipole is also in the direction like this, because the dipole moment is from negative charge towards the positive charge. Any one of you remember this? The electric field due to this dipole, in this case, if I write it vectorly, was 2 times k into p vector by r cube, vectorly if I am talking about. K was 1 by 4 pi epsilon naught, so it becomes 1 by 2 pi p vector, which is the dipole moment, divided by r cube. This was the formula of electric field created by a dipole at any axial point. If I don't write it in vector form, I can simply write if I don't want to write it in a vector form, I can simply write electric field will be P by, oh, I've missed epsilon naught. P by 2 pi epsilon naught R cube. That was the formula of electric field due to a dipole, electric dipole at any axial point. On the right hand side, what we are going to do, we are going to write the magnetic field due to a bar magnet. If you don't want to call it a bar magnet, you can call it as a magnetic dipole. Magnetic field due to a bar magnet at point A, axial point. Can anyone tell me what will be the formula for this? Can anyone tell me what will be the formula for this? So I've drawn a bar magnet, small bar magnet. This is the south pole, this is the north pole, and the point P is here, and the distance is always given from the center as R. The direction of magnetic field will also be like this, B vector. The dipole moment is like this. The dipole moment is M vector. It is from north, south towards north. What is the value of this magnetic field? Anyone would like to tell me? The value of magnetic field vectorly will be how much? Mu naught by 2 pi M vector divided by R cube. So you can see both the formulae are exactly similar. Both the formulae are exactly similar. You look at this, or you look at this, or you look at this. Both the formulae are exactly similar. If I don't want to write it in the vector form, I only want to write it as B. So I can write it as mu naught by 2 pi M by R cube. Here I have taken out the vector sign. You must remember that this magnetic field or this electric field is always in the direction of the magnetic dipole moment. This was the magnetic field or electric field due to a electric dipole, or in this case due to a magnetic dipole at any axial point. Have you noted this down?
Yes, sir.
Yes, sir.
Then the next thing is electric. Oops. On the left hand side, we have the second case, B, equatorial. Equatorial point. Now, what do you mean by equatorial point? Don't get confused. This is the dipole, plus Q, minus Q. Equatorial point means perpendicular bisector. So this point P is here, and the distance from the center is given as R. Let me just draw the diagram in that sense only. Let me write the minus Q sign here and plus Q sign here. Now you can see the dipole moment is like this, but here the electric field will be going in the reverse direction. If I want to write the electric field for this one, I will write in vector minus Kp by R cube. Minus sign indicates that it is going in the reverse direction. The value of K is 1 by 4 pi epsilon naught. So I can write this in this form also. Electric field is minus P vector divided by 4 pi epsilon naught R cubed. So So no matter how you write it, you are writing the same thing. You may call it a different form, but you are writing the same thing. I hope you are able to understand what I am doing here. If I talk about the bar magnet, then and I make the bar magnet like this: south, north, point P, equatorial point. You can also see the magnetic moment is like this, but the magnetic field will be like this. And I can straight away write magnetic field B will be equal to minus mu naught by 4 pi m vector divided by r cube, because this m vector is going like this, same as p vector, but the the magnetic field is coming in the opposite direction. Do we understand this?
Yes, sir.
This is magnetic field and electric field at the equatorial point. Have you noted it down? Noted down, everyone?
Yes, sir.
Then the last thing that remains is to see the formula for any general point. We will do it quickly. Just have to see the formula. This is minus q, this is plus q, and this is a general point at any angle theta. This is the point P. The distance of this point P from the center is r. The electric field will go like this at some angle phi. The electric field will go like this at some angle phi. You just need to remember the formula. The value of electric field will be given by P by 4 pi epsilon naught r cube into root over 1 plus 3 cos square theta. That is the value of electric field at any general point. At any general point, the value of this electric field. You must also remember the formula of this tan phi. This tan phi, the angle it makes is tan theta by 2. A very important result that you must remember. Tan phi is tan theta by 2. You can make the result here also quickly. General point, and I will just paste the diagram here. I have a diagram. I'll just paste the diagram here. This is the general point, and this is the direction of the net field B. It makes an angle phi. The value of this magnetic field B, no prizes, it's the same mu naught by 4 pi r cube multiplied by root over 1 plus 3 cos square theta. And the value of this tan phi is equal to tan theta by 2. As you can see, there is absolutely no difference between the two. Have we understood this? They're absolutely photocopies, xeroxes of each other. So if you understand one, you understand the other one as well. This is all about magnetic field that we need to know to start off the proceeding. Everyone has understood what we have done here? Yes or no? Okay, that finishes this class. I hope you have understood. In the next class, we'll go ahead and see what this magnet does. It creates magnetic field. We will see. The name of the chapter is magnetic effects of current. We will see, can current do the same thing? When I say current can do the same thing, what I mean is, can current also create magnetic field? That is the chapter that we are going to deal with. So I'll end this class today here. I hope you have understood this. If you have any doubts, anything, please let me know. Bye bye. Take care and God bless all of you.